guys, it's Manaswi, and before I get into the calculations of how we solved the problem, I'm going to discuss a few different background context pieces that you need to know. So first up, we have Ohm's law, which describes the relationship between voltage, current, and resistance. And it uses this formula to describe that relationship within a resistor. Next, we have Kirchhoff's law, which has two different parts. The first part is Kirchhoff's voltage law, or KVL, which states that the sum of all energy changes must equal zero. Then, for the second part, you have Kirchhoff's current law, or KCL, which is the sum of the current entering a junction must be equal to the sum of the current exiting the junction, which is depicted in this statement right here. Next, we have our variable definitions. We have current, voltage, and resistance, which are all different circuit elements. And current is represented by this lowercase I, and it is the rate of flow of electricity, which is measured in amperes, which is this capital A. Next, we have voltage, which is the lowercase v, and this is the electrical pressure needed to push the current, the electrical current, through the circuit. And it's represented with a capital V for volts. After that, we have resistance, which is represented as a capital R. And resistors are the obstacle that opposes or disrupts the flow of electricity. And they're represented with a capital omega, also known as ohms. Thank you.
Hello everyone, my name is Angie Reyes and I will be doing section B. I will be explaining how I got the KVL equations for the circuit. Before writing KVL, I first rewrote our resistor voltages using Ohm's law. Since we need each resistor voltage in terms of current, we will use voltage equals resistance times current, leading to the following equations. This last one has two currents because it is shared by both loops. For part B, I applied Kirchhoff's voltage law, which says that the sum of all voltages around a loop equals zero. We can write two independent KVL equations, one for each loop. For the left loop, the sum of all voltage drops must equal 4 volts, the source voltage. The voltage drop for R1 is equal to 6200 IA, and for R3 is negative 8200. That gives the equation 6200 IA plus 8200 times IA minus IB equals 4. Once we rearrange and distribute, we will get 14,400 IA minus 8,200 IB. Now, for the right loop, we see that the voltage drop across 3R and R2 must equal the source voltage, 2.5B. Voltage drop across R2 equals 4,700 IB. Voltage drop across R3 equals 8,200. But since the current direction is opposite, it will be negative. From there, we get the following equation. After distributing and rearranging, we get negative 8,200 IA plus 12,900 IB equals 2.5. Now, we have two equations with two unknown currents. For the next step, we will solve both equations simultaneously. We have IA equals 6.083 times 10 with a negative 4 exponent, which equals to 608.3 microamperes. For IB, we have 5.804 times 10 with a negative 4 exponent, in which A equals 580.5 microamperes. Both currents are very small, but that makes sense because the resistances are in the kilo-ohm range.
Hello, my name is Eric and I'll be doing part C of the assignment. I will be explaining the KCL relationship. The equation we have is R3 equals IA minus IB equals 27.84 mu ampere. This means only a small current flows down through the middle resistor R3.
Hello, my name is Deishel and I'm gonna be doing step 5. So this is me, power absorbed by the third resistor is power is equal current square times resistance. So this is me, power of the third resistor is equal 27.84 microampere square times 8,200 ohms. this is equal 6.37 microwatt.